Hi guys, and welcome back. So we are starting something brand new today. It is still technically within chapter 8. We're kind of doing the first half of chapter 8 now. The first half of chapter 8 is talking about quadratic functions, all right, which is slightly different than quadratic equations just because we're talking more about graphing this time. All right, so we are going to get into graphing at some point over these next several days. So I probably will end up giving you guys copies of graph paper, but if you need to get your hands on some graph paper, might be a good idea to do so before then. Before that, though, we're just talking about some basics about quadratic functions. I'm sure you guys can see if you look at the digital copies of the notes that I post. It does look like a lot, today's stuff, but I really don't think it's going to be that bad. It's just a bunch of different problems. It's pretty vocab heavy, but I really don't think it's going to be too difficult or too time consuming. But if anybody does look in the textbook, most of this is coming from section 8.2. All right, we're skipping over section 8.1 because we've talked a lot about quadratics and what quadratic equations are. So understanding quadratic functions, I don't think is too bad. What you would really need to know from that section is just that a quadratic function is like the graph of a quadratic equation, right? We know quadratic equations, their highest exponent is 2. So that's what that says here. What this is the most basic type of quadratic function that you're ever going to see. This is the y equals x squared function. It's called a parent function. You guys will probably learn more about that, if not towards the end of the year when you guys get to Algebra 2 in a couple years. But the shape, I think we might have mentioned it sometimes. I think you guys might be familiar with this. The shape is a parabola. All right, so we're completely veering away from slope-intercept form, y equals mx plus b, if you guys remember that. It's pretty much completely different. All right. So before we get into any other new stuff, I just want to talk real quick about factoring, or review it. All right, you guys just took your solving quadratic equations checks, so this shouldn't be news to you, or it shouldn't be very difficult. If we're asked to solve this quadratic equation by factoring, I'm sure you guys remember the very first thing we would have to do or have to look for is a GCF. All right. So are these coefficients 2 and negative 18 divisible by the same thing? If you remember this setup. Well, yeah, they are. 2 and negative 18 are both divisible by 2. So when you do that, you're left with 1 and negative 9. You wouldn't be able to keep going, and the two terms don't have any variables in common. So the GCF is just 2, and you're left with x squared minus 9, all that equals 0, okay? Then what you would want to do is you'd want to try to factor this, all right? I think you saw from your review sheets that this is a difference of squares problem, all right? Exponents are even, all coefficients are perfect squares, there's a subtraction sign, so we're able to factor this using difference of squares. Your 2 parentheses, x squared breaks down into x and x. 9 is a perfect square. It's 3 and 3. And then 1 plus 1 minus. Don't forget about the 2. And then equals 0. I'm going to do the rest of this on this side. All right. Then comes the zero product property. All right. Because you already have everything equal to 0, you're able to take all 3 things and separate them into 3 different equations, all equal to 0. So 2 equals 0. X plus 3 equals 0, x minus 3 equals 0. Now, 2 equals 0 doesn't make any sense. There's no way that 2 equals 0 is ever going to be possible. All right, so the only reason why we took out the 2 over here is to make our lives easier when we were factoring. But when we actually go in and solve it, it's not relevant. All right, because we're solving a quadratic, we're still only going to get 2 answers maximum, and that comes from these 2 equations that we can then solve because they both have a variable. So minus 3, x is negative 3, plus 3, and x is 3. All right, that's your review of factoring. All right, Okay, I'm going to keep this off to the side, all right? Because this is what the graph of y equals 2x squared minus 18 is going to look like, all right? If you actually sat there and plotted it on a piece of graph paper, all right? And the question is, what do you notice about the graph and the solutions to the equation? Well, what do you notice about the graph first? All right, it kind of looks like your parabola shape, sort of in the middle. We have this point down here. That's going to come in a little bit later, all right? The fact that we have minus 18 in the equation and minus 18 all the way down here. That's our y-intercept. But what you can also pick out from the graph along with this y-intercept of negative 18 is the x-intercepts. If you guys remember, the x-intercepts are where the graph crosses the x-axis. It was the same thing for the y-intercept down here. What are the x-intercepts? They're negative 3 and 3. And how does that relate to the solutions of the equation? Well, when we solved the last equation by factoring, the solutions we got to the equation were negative 3 and 3. And those perfectly match up with our x-intercepts. So maybe those two things have something to do with each other. And they absolutely do. All right? Again, recall that an x-intercept of a function is the value of x when y equals 0. So, by definition, x-intercept is where your graph crosses the x-axis. But in terms of values, y is always going to be 0 for your x-intercept. All right? So, a 0 of a function is an x value that makes the function equal to 0. All right? So, it also says there a 0 of a function is the same as an x-intercept of a function. When you talk about zeros a whole lot more in Algebra 2, sometimes, what was I going to say? You know, 0 is a much more, like, I don't know. I don't want to say, like, fancy word, but once you guys get to Algebra 2 in a couple years, I think they use 0 a lot more than x-intercept, all right? But in this case, when we're still in Algebra 1, I think we use zeros and x-intercepts pretty interchangeably. So if you ever see what are the zeros, plural, of a function, it's talking about the x-intercept, all right? And same kind of thing like with quadratic equations. We saw over the last several days that quadratic equations can have 1, 2, or no solutions. Because those correspond to the zeros or the x-intercepts of the function, a quadratic function may have 1, 2, or no zeros. So, again, it looks like a lot, but it's just pretty basic. All right? All we're asked to do is figure out what the zeros are of the graph just by looking at it. And again, zeros mean x-intercepts. So, where does the line cross the x-axis? At those 2 points that I just marked in black. All right? So, the x values of those points are 2 and 4. But because we're talking about zeros and x-intercepts, as you guys remember, I was a really big stickler about writing intercepts as ordered pairs. All right? So, that's going to continue into this chapter, or into these two sections. All right? If the actual numbers themselves are 2 and 4, the zeros, the actual points, are 2, 0 and 4, 0. All right? And that's it for this problem. All right? So here, where does this red line cross the x-axis? Well, right here at x equals 3. In this case, like we saw, like I said before, there's only one 0. There's only one x-intercept. All right? So the only 0 here is 3, 0. And for this, again, zeros are x-intercepts, so where does the line cross the x-axis, which is your horizontal one, if you forgot? It doesn't cross the x-axis at all, right? So if we were talking about the solutions to this hypothetical quadratic equation, there wouldn't be any, all right? So what are the zeros? There are none, all right? So I would rather you say something like none. Ooh, there we go. I'd rather you say something like none or no zeros rather than no solution, all right? Because we're talking about the zeros of a function rather than solutions to an equation. All right, and I think that's pretty straightforward, so I'm going to skip this, and again, as usual, you'll see the answer to this when you look at the digital copy of these solutions. All right? Okay. Another thing that we can talk about is the direction. All right? Obviously, if you have a picture, you're able to tell whether the parabola, excuse my hands, if I was in person, I would definitely be doing a lot of like bowl opening up like this or bowl opening down like that. All right? So like if you have a normal sized, not a normal size, like this is like a bowl, right? That you guys know bowls. So like parabolas look like this most of the time, right? They're like bowl shapes and they open up because that's how bowls normally operate. But sometimes they can go in the opposite direction and they would open downward like this. All right? So obviously you can tell something like that from a picture, but you can also tell whether a parabola is going to open upwards or downwards by its equation. All right? If you have a quadratic function or a quadratic equation written in standard form, which again looks like this, it's that leading coefficient that's going to tell you what direction your parabola is going to open. Okay? And again, like I think we saw this with discriminant. The number itself doesn't matter. All that matters is the sign of whatever this leading coefficient, this a value is. If a is positive, your parabola is going to open up. And if your a value is negative, then your parabola is going to open down. All right, the only thing that you would have to worry about is making sure that your quadratic function is written in standard form first. So, tell whether the graph of the quadratic function opens upward or downward. Explain. Okay, well, this would need to be in standard form before we could do anything, which it already is. All right, so all we're looking at is the a value, which is -4. And in this case, we're focusing on the sign of the a value, which is negative. So because a is negative, the function would open down. And that would be our explanation. All right, it opens down because a is negative. Okay? All right, this one is not in standard form. All right, so we're just going to have to do a little bit of moving around before we could think about this. Remember, standard form of a polynomial, the exponents are written in order from greatest to least. And you have to be careful with your signs. Make sure they follow if you move anything around. So since this is minus 3x squared, when we rewrite it, we're going to keep that minus with the 3x squared. And then 5x is positive, so we're going to leave it positive 5x. And now it's in standard form, and now we can figure out whether the graph will open up or down. And since, again, your a, your leading coefficient, is negative, it's once again going to open down for the exact same reason. All right. Now, this also technically is not in standard form because if you look over on the left side, we do have an x, all right? We do still want, with functions, we still have things in terms of y and x, but, kind of like how we had y equals mx plus b. We had y equals when we were talking about stuff like that. So we still want a y equals when we're dealing with quadratic functions. All right, so we're going to want to get y by itself as well first, all right, in addition to rewriting some things in standard form. So we're going to want to move this x over, all right, and I put this x in the middle right here because that's where it's going to go when we rewrite it in standard form. We have x squared, x to the first, and then your constant. So the degree on it would be 0, if you guys don't remember that. So y equals 4x squared plus x minus 8. And then again, we're focusing on the a value, which is positive 4. So it would open up because a is positive. All right? Okay. And this one is very similar to the last one. You would just have to move the 5x squared over. Again, for the sake of time, since this is actually a longer video than I thought it was going to be, I'll do this a little bit later. All right, a couple more things. That point that I had mentioned earlier, well, if you guys kind of, actually, rewind. I mean, you can kind of see this again visually with your bowl shapes. Bowls like this, these curves, have a highest point or a lowest point depending on whether they're facing up or down. All right, so this highest or lowest point is called the vertex of your parabola. All right, and all of these things kind of go together when you look at it visually. All right, if your parabola or if your bowl opens up, your vertex is going to be at the bottom of the bowl. All right, so your vertex is then the lowest point. And since it's the lowest point, we would call it the minimum. All right, that's what minimum means. It's the smallest. If your parabola is opening down, now it kind of looks like an upside down bowl or maybe like a hill instead. So if you have your hill shape, your vertex then is going to be the top of the hill. Now it's the highest point. So highest point, we call that a maximum. All right. The other thing that goes along with the vertex, all right, if you guys can kind of see from all of these pictures, your vertex, hold on. There we go. Your vertex kind of looks like it's directly in the middle of the parabola, all right, which it is. So your vertex would split your parabola in half, all right? So you can draw an invisible, sort of invisible line. That's what's in green, through your vertex between the parabola that does split it in half, all right? I don't know if you guys remember doing these types of things, maybe in like elementary school where you talked about symmetry, how when a figure is symmetric, it looks exactly the same on one side as it does on the other, all right? Like if you kind of folded this graph over itself, the arrows and all of the points would touch each other really, really nicely. All right. So that's what we mean when we're talking about the axis of symmetry. All right. You don't really need it as part of your final like graph of the parabola. But it is a really, really useful thing. All right. To help you when you create these graphs. The axis of symmetry is a vertical line that divides a parabola into two symmetrical halves. All right. As I said, it always passes through the vertex of the parabola. And again, we're mostly talking about things, from a visual perspective. All right. So they talk about two ways to do it. One way is just to kind of look at it, and then the other way is to find the average of the two x values of your zeros, since the vertex is going to be exactly in the middle. All right. I personally, since we're just talking about like visual stuff, I think it's just way easier to look at all of this from a visual perspective. This does work most of the time, so if you want to do something like this, if that makes more sense to you, absolutely go for it. But the other thing I want to talk about really quick before we do some problems is the fact that regardless of whether or not your parabola opens up or down, your axis of symmetry is always going to be a vertical line. All right, I guarantee that. There will never not be a time where your axis of symmetry is horizontal. It's always going to be vertical, okay? So when the question asks you for the axis of symmetry, because we're talking about a line now, I'm going to be looking for the equation of a line, all right? So if we're talking about writing the equation of a vertical line, I don't know if you guys remember, okay, we're good. This Hoy-Vux thing. Okay, if you don't, really quick, horizontal lines have a zero slope and their equations are y equals. Vertical lines have an undefined slope and their equations are x equals. So if we're always writing the equation of a vertical line, the equations of the axis of symmetry are always going to be x equals something. And since the axis of symmetry passes through the vertex, the equation is always going to be x equals whatever the x value of your vertex is. All right, as you can see here, And as you can see here, because this vertex would be -2, -4, and the axis of symmetry is x equals -2. All right? So, if we talk about this, all right? Now we're doing everything that we've talked about. Zeros, vertex, and axis of symmetry. All right? Zeros. Where does the red parabola cross the x-axis? Nowhere. So what are the zeros? None. Vertex. What's the highest point of the top of the hill or the bottom of the bowl? All right, highest point or lowest point. Lucky for us, the vertex is actually marked off with this nice dot. All right, so what point is that? -1, 2, 3, 1, 2. All right, the vertex is -3, 2. And the axis of symmetry. You'll usually see me use the abbreviation AOS for axis of symmetry. You can absolutely use it too if you want. And again, the axis of symmetry is, if I actually drew it in, it would pass through the vertex, and it would be a vertical line that splits the parabola in half. All right? And the equation, since it's a vertical line, would be x equals whatever the x value of your vertex is, which we just found is 3. So the axis of symmetry is x equals -3. And that's it for the problem. So, if we do this again, now we actually have zeros this time. The places where our graph crosses the x-axis are right here at 2 and 4. So our zeros are 2, 0 and 4, 0. What's your vertex? It's the highest or the lowest point of the graph, which again is marked off right here. That's 1, 2, 3, -1. And the axis of symmetry, if I drew it in, it would be right there. Vertical line, x equals 3, because that's the x value of our vertex. Okay? Again, the same thing, so I think I'm going to skip this, and I'm going to do it later. And I believe this is the last thing we have to talk about. All right, domain and range, specifically with dealing with quadratic functions. All right, if you guys don't remember, when we talk about domain in general, domain is just all the possible x values, and range is all the possible y values. All right, so these arrows up top, I might have mentioned this a really long time ago, but these arrows up top not only go up, but also out. All right, so your quadratic function is not only going up forever, but it's also going out, left and right, in either direction forever. And that's going to happen pretty much every single time. So unless you're told otherwise, x, because it's going in both directions forever, x can be anything you want. So the domain of a quadratic function, unless you're told otherwise, is always going to be all real numbers. Okay? Range is going to be different though, all right? Because we just talked about the vertex, there is going to be a highest and a highest or lowest point, all right? In general, it starts at the vertex, all right? Okay, it starts at the vertex, all right? Range, again, we're talking about the y value, so we're always focusing on whatever the y value of your vertex is. So it's got something to do with 1, all right? This point is always going to be filled in, all right? So when we talk about like inequalities and stuff, if you guys remember writing, I think we had done this a really long time ago, writing like the domain and range for stuff like this, a filled in point when you talk about inequalities is either less than or equal to or greater than or equal to. You would need that line underneath the inequality symbol, all right? So your options for writing the range are either less than or equal to, or greater than or equal to. All right? And figuring out which one, I think is pretty straightforward. If it's going up, you know, your y values are going up. So all of the other y values are going to be bigger than 1. 1 is your smallest. Everything else is bigger. So the range of this function right here is going to be y is greater than or equal to 1. because all the other y values that you would have in the picture are bigger than 1, including 1. If your parabola opened down, and this was still your vertex, let's say, everything or all of your y values would be going down, so it would be less than 1. All right, you would still include 1 because of that filled in closed circle, but then instead of greater than or equal to 1, it would be less than or equal to 1. All right, I think this might make a little bit more sense when we do a couple problems like this. But as I keep saying, definitely reach out by whatever means you're most comfortable with, and I'm more than willing to help you out. Okay? So we're kind of doing everything all at once. All right? Zeros. Where does our red parabola cross the x-axis? It doesn't. So there are no zeros. Vertex, the highest or the lowest point, is right here in red. So 1, 2, 3, 4, -5, 1, 2, -3. All right, axis of symmetry is this vertical line that passes through the vertex. It's a vertical line, so it's going to be x equals whatever the x value of your vertex is. So it's -5. Excuse me. And then, as I said before, unless otherwise specified, your domain is always going to be all real numbers. So that's the case here. Range, now we're talking about the y values. All right, so we have y. It's got to have something to do with the y value of our vertex. So we know it's going to be something in terms of -3. All right, we're going to have that or equal to sign in our inequality because of the filled in circle. And how does it open? It opens down. All right, so since it opens down, all the y values are less than -3. So y is less than or equal to -3. And that's everything we need for this problem. All right? So, for this, what are the zeros? Again, there's nowhere where it crosses the x-axis, so none. What's our vertex? The highest or the lowest point, which is right here. So that is 2, 1. Our axis of symmetry is this vertical line. So that's going to be x equals whatever the x value of our vertex is, which is 2. Domain is all possible x values. So because we aren't specified otherwise, it's going to be all real numbers again. And then we're going to talk about the range. So range again deals with the y. It's something in terms of this y value of the vertex, so we can put that 1 in there. And then how do we figure this out? Which direction is it opening? All right, well, it's opening up. We have that filled in point, and it's opening up. So all the y values are going to be bigger than 1. So y is not just greater than 1, but because of that filled in point down here, y is greater than or equal to 1. Okay? Okay. Now we actually have some zeros. That's really the only reason why I wanted to do this problem as well. Because we have some places where the function crosses the x-axis. Our zeros are -3, 0 and -1, 0. Our vertex is either your highest or your lowest point, so that's down here. It's -2, -2. Our axis of symmetry splits the parabola in half. It's a vertical line, so its equation is x equals whatever the x value of your vertex is. It's -2. Domain, we're not given any other specification, so we can say it's all real numbers. That's easy. And range. Range deals with the y. It deals with whatever y, the y value of your vertex is, which is also -2. And then the rest of it goes into which direction the parabola opens. So since it opens up, again, all the y values are going to be bigger than that -2 on the vertex. So our range is going to be y is greater than or equal to -2, again, because of this filled in point down here at the vertex. If for whatever reason you had an open circle, it would be greater than or less than, all right? But then that would change the domain, and like things would probably get really, really not really tricky, but like slightly more complicated than anything that we've talked about in this video. All right, so that's all I've got for you for today. Again, reach out however you feel you need to if you have any questions. But yeah, that's it. Talk to you guys soon.